So here is the question in front of you and we are going to solve it. Okay, let's read the statement first. Which of the following isoelectronic ions, okay, have the lowest ionization energy? Lowest. Isoelectronic, that means all four options given over here, they should have same number of electrons. Isoelectronic. Okay. Lowest ionization energy. So how the concept is going to flow? Try to understand this thing. Lowest ionization. What is this ionization? Is you are trying to remove the outermost electron from the isolated gaseous atom or ion, right? Okay. So if you understand one important thing, if the effective nuclear charge is minimum on the outermost electron, then the ionization energy is going to be minimum. This factor is going to play the most important role over here. So let's see, let's write the number of protons and number of electrons in each one of them. Let's write the protons and electrons. So sodium, atomic number 11, proton is going to be 11 and it has a positive charge, 1 unit positive charge. That means 1 electron is lost. In neutral atom, it was 11, 1 electron lost, 10 electrons. Similarly, magnesium, atomic number 12, plus 2 unit charge, 2 electrons lost, 10. See, this number is going to be 10 every time. Why? Isoelectronic. Okay. So we just need to focus on number of protons, that is 9 in fluorine and 8 in oxygen. Now try to understand this thing. If the number of protons in the nucleus is less or the minimum, then the effective nuclear charge in all these four cases on the outermost electron is going to be minimum. What do I say? I'll repeat it once more. If the effective nuclear charge is minimum, then the ionization energy is going to be minimum, and that is why option D is the right answer. Let's recall the concept. If number of protons in the nucleus is less or the least, then the effective nuclear charge is going to be minimum, and then the ionization energy is going to be lowest. So option D, oxide ion, O2 minus, 8 protons, 10 electron. Lowest ionization energy. So D for Delhi or D for Denmark is going to be the right answer to this question. And with that, we conclude this question. So here we have a very nature-loving question in front of us. Let's see what the question says. Which of the following characteristics of metals cannot be explained, okay, by electron C model of atoms or metals? Electron C model of metals, okay. And the option says hardness, malleability, electrical conductivity, and sonorousness. Okay. So let's first understand this electron C model of metals. What generally happens in a metal crystal, the metal tends to lose the valence electrons, and metals are present in the form of kernels inside the lattice at lattice points, right? And the free mobile electrons, they behave like a sea of electrons, right? I hope you can understand this. This is your kernel, the positively charged metal ion, and this is your sea of electrons, right? They are mobile electrons. They can move in the crystal, right? So the question demands that we have to figure out which of the following characteristics cannot be explained by this model. So hardness. Now what is the reason behind the hardness? Is the stronger the attraction between the kernel and the electron, the stronger is going to be, the harder is going to be the crystal. So hardness can be clearly explained with the electron C model, right? Malleability. Okay, what is malleability? Basically, it is the tendency of the metals to convert into sheets when they are beaten up, right? This is exactly opposite to crystalline nature. when you beat a crystalline substance, that usually breaks, that breaks into pieces. But this is not the case with metals. Generally, metals are very malleable. Gold, silver, they are very malleable metals. That means you can convert these metal into thin sheets. Now, what is the factor that is the playing role in it? That when you beat up a metal, then the kernels, they adjust their location. They adjust their location according to the pressure applied. So malleability is also explained by the electron C model. We are talking about kernel, we are talking about the interaction, the changing interaction between them, right? Okay. Electrical conductivity. I hope this is the simplest option. You know the reason behind the electrical conductivity. Metals are highly electrical conducting in nature. And why? Because they have sea of electrons. They have huge number of electrons, free mobile electrons in their crystal, which can move from one location to another. And the movement of electron is nothing but conduction, electrical conduction. Okay. So the only option left is sonorous. Sonorosity is basically the production of sound. When you hit a metal, if you hit a metal, then it produces sound, and that is because of the vibrations that is being produced. So electron C model is not explaining this characteristic sonorousness of the metal. So option D for Delhi or Denmark or any other place like Dehradun is going to be the right answer to this question. And with that, we conclude this question. Yeah, so here is the question, and this is like from kinetic theory of gases. And let's see what the question says. Helium atom is 2 times heavier than a hydrogen molecule. We already know this concept. The mass of helium is 4, hydrogen is hydrogen molecule, so 1 into 2 is 2. Okay. At 298 Kelvin, the average kinetic energy of helium atom is, okay, and the option says 2 times that of hydrogen molecule, okay, half, 4 times, or same. Okay, so this is the comparison between helium atom and hydrogen molecule in terms of average kinetic energy. I hope you remember that average kinetic energy can be calculated by the formula 3 by 2 kT, right? Where K is the Boltzmann constant, which can also be written as the gas constant R divided by Avogadro's number Na into T, right? So these are the formulas we generally use for the average kinetic energy of a molecule or an atom. Okay. Now there is a comparison between helium, whose mass is 4, as compared to hydrogen. But if you observe carefully that there is no term in these formulas that relate molar mass with the kinetic energy. The kinetic energy is a function of temperature. Okay. So can we say that either it be helium atom or hydrogen atom, if the temperature is constant, the kinetic energy or the average kinetic energy is going to be same. So the option D, same as that of hydrogen molecule, is going to be the right answer. So with that, we conclude this question. Okay, so here is the question, and this is a concept based question. Let's see what the question says. The enthalpy change of a reaction does not depend on enthalpy change. That means it is talking about delta H. Fine. See, what we know about delta H is that it is a state function. Okay. So what is a state function? There are two types of function. One is state function, another one is path function. As the name suggests, the state function depends on the initial and the final stage only. Does not depend on the path, does not depend on the intermediates, right? And the path function, like the heat, it is going to depend on the path that is followed. If you change the course of the path, then the path function is of course going to change. Okay. Let's see the options one by one and figure out which is going to be the right answer. The initial and the final enthalpy changes of the reaction. Of course, yes, enthalpy change, a state function, is going to depend on the initial and final enthalpy change. How do you write delta H for the reaction? It is summation of enthalpy of product minus summation of enthalpy of reactant, right? This is how you write the formula. Okay, so A option depends. A option, the condition given in A option, that is related to enthalpy change, right? So we are looking for which does not depend. So A cannot be the answer. The state of reactants and the products. State of the reactant and product. So how you gonna say that? Let's say that H2O solid converts into H2O liquid. The state is changing. So enthalpy change of this reaction is going to be some value. We are not concerned of that value. Is it going to be positive or negative? But there will be some value for this reaction, this state change of state. This is basically solid to liquid. So this is melting, or you can call it fusion, right? So this is enthalpy of fusion, and we know this value is not zero at all, right? So yes, the state of the reactants and product, this is also dependent on the enthalpy change, or enthalpy change is dependent on state of reactant and product. Option B cannot be the answer. The different intermediate reactions. Okay, fine. Let's understand this with the help of graphical representation. Let's say this is a graph in between enthalpy and the progress of reaction. Okay. So what do I say? Let's say the reactant is A, and it passes through an intermediate and finally converts into the product B. Okay, this is one way the reaction is proceeding. The another way, we are going to form A to B only, but the mechanism is going to change. This time, let's say we have two intermediates, and finally we are moving to stage B, right? Here we have intermediate 1 and intermediate 2, right? And in the first path we have intermediate 3, right? So what do I say is, what is the enthalpy change in this? Enthalpy change is going to be this value, delta H, and this value is independent of the fact that we have two intermediates, that is the red mechanism, or we have only one intermediate, that is the yellow mechanism. It is independent of this fact. Enthalpy change independent of the intermediates, independent of the path. It only depends on the initial state A and final state B, the change of enthalpy, right? This is independent of the path. So we can say that the different intermediate reactions, this is not going to hamper the enthalpy change. That means C should be the probable answer. Let's look for option D as well. The nature of the reactants and product. Okay. See, try to understand this thing, that let's say we are moving from carbon graphite to carbon diamond. Okay. Carbon is in solid state in both the cases, but the nature of the reactant and product is going to differ. Graphite is different from diamond. The properties changes, the properties are different, and there is some enthalpy change in the reaction, right? There is some enthalpy change. So we can say that enthalpy change of reaction does depends on the nature of the reactant and the product. So option D cannot be the answer. So we are looking for that option which does not depend on the enthalpy change. That means different intermediate reactions. If you have different intermediate reactions, that is not going to change the enthalpy change. So option C is going to be the right answer to this question, and with that we conclude this question. Yeah, so here we have a beautiful numerical from ionic equilibrium. Let's see what the question says. The dissociation constant for H2S, okay, and HS minus are 10 to the power minus 7 and 10 to the power minus 13 respectively. One thing that has to be observed is that there is a huge difference between the Ka of H2S, that is the dissociation constant of H2S, and dissociation constant of HS minus. Let's call it as Ka1 and this as Ka2. So what I am trying to say is Ka1 is really very high as compared to Ka2, right? Okay. The pH of 0.1 molar aqueous solution of H2S will be. Okay. So we are looking for the pH. The options are 4, 5, 3 and 2.5. So we are only and only concerned about the H plus concentration in H2S and HS minus, right? But I'm very not sure of this fact that the HS minus is going to contribute significantly to the H plus concentration. Why? Because the Ka2 value, that is 10 to the power minus 13, is way too small as compared to Ka1 value, that is 10 to the power minus 7. Okay, but let's try solving it. We'll see to it further. H2S is going to dissociate into H plus and HS minus, right? So if I say initially it was 1 H2S 1 mole, then it is going to be 0 and 0 here. Dissociated, let's say that out of 1 alpha H2S got dissociated, then alpha H plus is going to form and alpha HS minus is going to form. This is according to the stoichiometric coefficient. So the left amount will be 1 minus alpha and alpha. And now let's generalize this for concentration C. If it was C concentration, multiply this whole with C. So if it initially was C concentration of H2S, then C alpha got dissociated and C alpha concentration of H plus and C alpha concentration of HS minus was formed. Perfect. If you need to write the Ka value for this, it is going to be what? Concentration of H plus into concentration of HS minus upon concentration of H2S, right? That makes sense. If you put the value, then it is going to be C alpha into C alpha upon C1 minus alpha. This is the Ka1 that we are talking about, right? C got cancelled, numerator, denominator. We are left with C alpha square upon 1 minus alpha. Now see, this alpha will be very small. We're gonna neglect this for the simple calculation. So from here, can I say that alpha is going to be under root Ka by C, right? Or rather Ka1 by C. Okay. The concentration of H plus is C alpha. So can I say that concentration of H plus, which is C alpha, will be C into under root Ka1 by C. If I multiply C and take it inside the under root, it will become Ka1 into C square by C. If I cancel it out, so my concentration of H plus from H2S is going to be Ka1 into C. Okay. Now try to understand this thing that H plus concentration and HS minus concentration is same. That is C alpha, C alpha. If I just further solve it by putting the values, Ka1 is given as 10 to the power minus 7 and C is 0.1, that means 10 to the power minus 1 is coming out to be 10 to the under root of 10 to the power minus 8, which is nothing but 10 to the power minus 4. Okay. This is one thing. This is concentration of H plus from H2S. Now let's talk about HS minus. On the same parallel basis, can I say that the concentration of H plus from here is again going to be Ka2 into C, or rather C2. The concentration of HS minus here is what? 10 to the power minus 4. It is same for H plus and HS minus in the first reaction. So can I say 10 to the power minus 13 into 10 to the power minus 4. This will give you the concentration of H plus from HS minus. You can clearly see that this value is going to be way too small as compared to 10 to the power minus 4 value, right? If you just want to see it further, minus 13, 4, minus 17, can I say 10 into minus 18, and this will be like root 10 into 10 to the power minus 9. Now minus 4 and minus 9, way too small. So what I'm going to do is I am going to neglect this value, right? I am not going to take into consideration while calculating the concentration of H plus. Now pH is going to be nothing but minus log of H plus, right? So can I say minus log of 10 to the power minus 4? Very simple. 4 minus 4 will come here. Minus minus will plus. 4 log 10 base 10. This is going to be 1. So answer is 4. Okay, this is your final answer. If you look at the options, what do I have? Option A, 4 is the right answer. So with that, we conclude this beautiful question. Thank you.